So we will see the difference between the supervised and unsupervised loss functions and introducing teaching neural networks with physics. So let's begin by defining the engine of truth of any machine learning model. So the mechanism of learning. In a typical setup, we have a task which is predicting an outcome based on an input state. That input goes into our black box or neural network, which spits out a prediction. We then have a performance measure that judges the objective distance between the prediction and an oracle of absolute truth. The crucial component linking these is the loss function. The loss function is the single mathematical mechanism that translates failure into an adjustment signal, telling the network how to update itself to get closer to the truth. So, the most universal measure of this loss is the MSE, or the mean squared error. It is formally the difference between the actual and the predicted output squared. So that's why the y hat minus the y minus the y hat. So as you can see here, our objective is to find the parameters that minimizes this across the entire dataset. So in classical deep learning calibration, we rely on the oracle paradigm. This is a strictly supervised mindset. The neural network acts as an inverse mapping tool. It takes the market inputs like the strikes and maturities and forces the output to matches the pre-calculated label. So we compute the supervised calibration loss over a training set of the surface and parameter pairs, trying to minimize the MSE between the predicted and the actual ground truth labels. But this reveals a crucial flaw. Like, where do those massive like data or volumes of data and labels come from? They require generating millions of synthetic Monte Carlo paths. So this reliance on this synthetic data leads to computational collapse of data matching for classical diffusive models with Markovian structure. We can use PDEs to solve calibration as a problem identification problem. But when we move to rough volatility models like the rough Bergomi model, we face the non-Markovian dynamics based on fractional Brownian motion. These lack a semi-martingale or affine structure, meaning standard PDE methods completely fail. Consequently, generating the massive synthetic training datasets required to act as the truth becomes a computational bottleneck. So to solve this, we introduce the physics paradigm, calibrating using unsupervised BSDEs. We transition from data matching, which depends on an external oracle for truth, to physics matching, which depends strictly on the internal rules of the system. So instead of generating massive synthetic datasets to teach the network mapping, we embed the mathematical rules of the financial market directly into the network architecture. We achieve this by leveraging the BSD equation, or the backward stochastic differential equation, representation of the pricing function. So we will see now the flow. This flow chart illustrates the process. We have a forward generation of the asset path state and the backward pull of the option price. In this setup, model parameters are not targets to be predicted. They are treated simply as tunable weights. So A forward Euler method initiates from market data, and the network simultaneously optimizes the BSDE solution and the model parameters in a unified dynamic training process. So we go both ways, forward and backward. To visualize this difference, so in a supervised system relying on labels, the model learns a direct inverse mapping. It's like forcing a puzzle pieces together into coordinate mapping to pre-calculated truth. So it knows what the answer is, but not why. In the physics approach, the model learns to navigate the stochastic environment. It never sees a pre-calculated label. It simply obeys the differential equations. If it follows the rules of the road, it inherently arrives at the correct destination. So, this paradigm shift matrix summarizes the transition. Supervised calibration requires external labels and massive synthetic datasets to perform a direct inverse mapping based on data-driven constraints. So the deep BSD calibration uses the terminal payoff as the source of truth, requires only the market's initial state, and jointly optimizes the parameter and the BSD solution. Using physics-driven constraints, this completely eliminates the data generation bottleneck by shifting the source of truth entirely. This means we must redefine our loss function as terminal misfit. We define the unsupervised BSDE terminal mismatch loss as the mean squared error between the true terminal payoff and the simulated terminal value obtained from our Euler march. In this unsupervised paradigm, MSE is no longer used to match parameters to a synthetic label. Instead, the loss function measures the discrepancy between where our stochastic paths actually end up and the undeniable, unbreakable physics of the financial contract. So this is the function of the true payoff and the simulated terminal value. This makes the payoff function the ultimate anchor, let's say. For standard European call option, the payoff is simply the mathematical function, which you know, like the maximum between ST and K and 0. The financial contract itself provides the only label required. So the loss is exactly the distance between where our stochastic paths land and what that rigid line is. If the model parameters and the BSD solution are correct, the paths align perfectly with the payoff. This is why the BSD loss requires absolutely no label parameters. The mathematical payoff function alone serves as the training signal, making synthetic dataset completely obsolete. So, to recap, we know the financial contract provides the only true label, and then the distance between the stochastic path where it lands and this rigid line, it's we calculate the loss function. Minimizing that, we learn the actual physical equation, let's say, or intuition of how these contracts are priced. We also have the theoretical guarantee backing this up. So theorems proves that the mean squared error between the model implied option prices and the actual market data is strictly bounded by this terminal loss function. By minimizing the terminal misfit, the mathematical guarantee is to calibrate the model accurately to the initial market state. This loss can be minimized to an arbitrary degree, limited only by the universal approximation capability of the neural network. So, now we see empirical validation proves this theory. In experiments using the S&P 500 data and the rough Bergomi model, the deep BSDE scheme achieves highly competitive error rates in a fraction of the time required by converged Monte Carlo methods. We observe a rapid decay of the objective function within the first 10 iterations, demonstrating incredibly stable and efficient optimization dynamics, all without using a single label. To conclude, this is the new reality of the market calibration. We have moved from data heavy to theory rich, eliminating the computational bottleneck of the synthetic data generation. Model parameters are no longer targets of an inverse mapping, they are variables optimized alongside the BSD equation. By trusting physics over oracles, the internal mathematics of the forward-backward SDE and the terminal payoff become our ultimate ground source of truth. Thank you.